Okay. Hello everyone. I hope you're doing great. So this is the second tutorial. Is there anybody here who came to this class last week and found it empty and didn't see our note? I just want to make sure if everyone was able to use it, attend to the tutorial session. Hi. Okay. So as you probably are aware of, you have the coursework. The coursework has been released. You have 2 weeks to do that, and after that it will be marked. It's 10%, I think, of your total mark, so make sure that you do it. It's just 2 questions, and it would be pity not to do that. So it's 10%, you might need it at the end. Okay? Any questions about the tutorial or the coursework? And also, we start the lab sessions next week. So lab sessions would be 5%, just attendance and participating in the lab is 5% of your final mark. So I encourage you to come to the lab sessions. You will receive an email on the week that you are supposed to have the lab. It's also on your timetable. Make sure that you attend to those sessions as well. There are There are 2 interesting experiments you can do on the lab sessions. Okay, so do you have any questions, any comments, anything you want to tell me? Any concerns maybe? If not, we will start then. We have 6 questions today, so I might go a little bit fast. Just tell me if there's any part you don't understand, and I will explain it to you. Okay, hi. So we'll start with the first question. As you can see here, the first question is giving you a figure, and the pressure at A is wanted. We know that we have water at some parts and mercury and some other parts, and the atmospheric pressure is also given to us. So we should start with the point that we know, that is PA. And we know, okay, so I guess you don't, maybe you need that. Okay. So I would start with the point that I am aware of, which is for me here point D. I know that PD is equal to atmospheric pressure, and using PD I can calculate the P at this point. So PC, which is also equal to PC prime, which is also equal to PC second, is equal to PD plus the density of the water that has filled this part of the tube, the water, the gravity, and we know that the height of this column is 25 centimeters, so we would use the meter. Okay, so we have the pressure of the point C here, here, and also here. Because air is filling this part of the tube, and air's density is relatively small to the density of water. Density of air is 1, density of water is 1,000. So we can neglect this pressure, this pressure difference. This is not 0, but this is very close to 0, so we neglect this column of air. And as for that, the pressure in this point would be equal to pressure in these points. As I've written here, PC is equal to C prime is equal to PC second. So going further, using the pressure at point C, I can calculate the pressure at B prime, which is also equal to pressure at B because they have equal height. So PB prime is equal to PB, which is equal to PC plus the hydrostatic pressure of the liquid here. So PC plus the density of mercury, gravity, 0.3 is the height of this part. And I know from the previous part that PC is equal to PD plus hydrostatic pressure of the water column. Now, using the pressure of point B, I can easily calculate the pressure at A. But the important thing here is that the pressure at B is bigger than the pressure at A. So PB is equal to PA plus the density of the water here. Using this, I can calculate the PA, which is equal to PV minus rho G 0.7. Yeah? Oh, yeah. Sorry. Okay. So now we have the PB from the previous part. So PA would be equal to the atmospheric pressure now we have all the parameters that we need to get the PA. Always make sure that you know if you are reporting the gauge pressure or the absolute pressure. Sometimes in the equation, the specific type of the pressure is mentioned. So if you are supposed to report the gauge pressure and you report the atmospheric pressure, you will lose marks. So always pay attention to this. This is very easy. It's just not worth it to lose marks for it. Okay? This was the first question. Do we have any questions?
We can leave it on there for just a second.
Okay.
What formula is it used?
Well, the only thing that we have used here is rho GH. So, right, yeah. If the density is not constant, we cannot use this rho GH. But now, because everything has constant density, rho GH is enough.
Could you please tell me about, once we get this kind of questions, like word message we need to use?
Sorry, what?
Like word message, like how can we start this kind of question?
Okay, let's move on to the second question. Okay, so in this question, the density is not constant. We have we have settling sediments in a tank. So because of the settlement, the density of the brackish water is not constant. As you go down the tank, the density increases. The equation to calculate the density is also given to you. And y is the depth below the free surface. This is important. So y direction is downward. Okay, so you would use the depth as y in this equation. What is the gauge pressure at the bottom of the tank? Is the liquid depth is 1 meter. All right, so we have like a tank here. So we have sediments, and as you go down, the sediments become more and more, so the density is increasing. Y is equal to 0, and the direction is downward. So This equation is given to us in the question. And we want to calculate the hydrostatic pressure. Okay. Okay, so now we cannot use the rho GH formula, so I have to go back one step and use this formula. You have seen this in the course, and use this to calculate the rho GH. If the density is constant, then a simple integration is done, and you would get H instead of this dy. So now I can integrate this and get delta P is equal to integral of rho G dy, and y is from 0 to L, which here in this question is 1 meter. So G is constant, it comes out of the integral, and the equation of the density is given to us, dy. And now I would get 1000 G. The integral of 1 is y, and the integral of y is y2 over 2. From 0 to 1. So I would get 1000 . Okay. Any questions? Yeah, this is the start point. Yeah, you have to know this. The most important thing is that the pressure changes with the height of the liquid. So this is just it. Okay, let's go to the next question. So, third question. Okay, this is an inclined manometer. The side pipe is having some inclination, so that the small amount of densities can be calculated with this. The important thing about the inclined manometers is that the angle is always low. So if in some questions you are doing the calculation as you find that the angle is like 45 degrees, it's definitely something wrong. It's something between 0 to 5 or 10% usually. So let's start. This is an inclined manometer and filled with oil of a specific gravity of 0.85, and the cistern is initially open to atmosphere. A pressure line is then connected that creates a gauge pressure of 500 pascals. So basically it's saying that this surface is initially in contact with the atmosphere, and now we are exerting a pressure equal to 500 pascal to it. And because we are increasing the pressure, the height of the liquid in the side pipe is increasing. You know, the amount of the liquid that has been displaced in the cylinder is now gone to the pipe, and the height of the liquid in the pipe has increased. So This increase is equal to 200 millimeter, and the unknown is the manometer angle, which is here. This is alpha. Okay, so make sure that you note that this line is B and the lower line is C, and the difference between point B and point C is delta H. So I would start with point B. Question 3. Okay, so PB is equal to rho GH, and the vertical component is important to us, but we have the D equal to 200 millimeters, so we need to convert it to the vertical and use the H instead. H is equal to D sine alpha, and this is the important thing for me. Using PB, I can calculate PC, because I now have the PB and I know the difference, the height difference is delta H. So I can now calculate PC using PB plus the hydrostatic pressure of delta H. PB is rho G D sine alpha plus rho G delta H. So, as I said, the volume of the oil that has been displaced from the cylinder is now gone to the tube. So, I would write volume of oil displaced and the volume of the displaced oil is the cross-sectional area multiplied by the height, and on the other side again the height multiplied by the cross-sectional area. A is the cross-sectional area of the cylinder, and this is A, the cross-sectional area of the tube. So using this, delta H would be equal to D A over A, and we know the cross-sectional area, the area for a circle is PR2 or P diameter over by 2 over 2. Okay, so the diameters are given in the diagram in the question sheet. One is 5 millimeter and the other one is 1 centimeter. So now I have the delta H based on relative to D. So using this, I can calculate PC. I know PC is equal to 500, and I know the rest of the parameters as well. So alpha would be equal to 2.825B. Okay? Any questions?
Can we see the question again?
Yeah, I'm trying to make it kind of, but it's not working. This is the question.
rho GH to rho G d sine alpha to find the pressure at B.
Okay. The pressure at point B is rho G d sine alpha. The first line is the PB is equal to rho GH, but H is the vertical height and we have the inclined length. So we use that inclined length to calculate the H, and then PB would be equal to rho GH.
And then to find the pressure at C, you have to add them together. Surely subtract.
You know, okay, here C is below B. So it would be the pressure at B plus the hydrostatic pressure of this liquid here, which has the height of delta H. So you need to add this together to get. Okay. So good, so far so good. Yeah?
What's the A over A?
Okay. Again here, A is the cross-section of the big part and the small a is the cross-sectional area of the smaller part.
Yes.
Okay?
I mean the change in A over the big A. The small b times small a over big A. Yeah, it's like change in height increase the
Okay. Okay. So you see the volume of the oil that has been displaced is now added to the tube. Okay. So A dot delta H is the volume of the oil here. Okay. And now it's added to the other part. Okay. For the sake of time, I will go to the next question. This is question number 4. We have a mercury manometer. The H is the height when the pressure inside the tank is 150 kilopascal. Absolute. This is very important. The pressure is given here to us in absolute form. So if the absolute pressure in the tank is increased by 50%, what will the percentage increase in HB? Okay, and the atmospheric pressure is 1 bar. The atmospheric pressure here is given to us because we have the absolute pressure. Okay, so all right. So in the initial state, before we add the pressure, we know that PA is 1 bar, which is equal to 10 to the power of 5 Newton per squared. So P would be equal to PA plus rho GH. I mean, you see P here is equal to atmospheric pressure plus the hydrostatic pressure of this column. Okay? So P would be equal to PA plus rho GH. And PA, we have that. This is given to us in the question. The pressure of the tank is equal to 150 kilopascal. Using this, I can calculate the rho GH. And rho GH would be 50 kilopascal. In the second stage, after we have added the pressure, so the second pressure is like the atmospheric pressure plus the new height. and we know that the P prime is equal to it has 50% increase. So if I multiply the 150 kilopascal given to us in the question by 1.5, I would get the secondary pressure. So using this, I can calculate the rho GH prime as and I would have 125 kilopascal. So the question has asked us the percentage increase in H. So how can I calculate that? I can subtract these two equations. So I would subtract okay, and I divide these two to get the percentage increase, which is defined as H prime minus H over H, and it's equal to 75 over 50, which is equal to 1.5. So it means that I have 50% increase in H. Okay? Any questions? Yeah.
I thought on the sheet though it said it was 150% increase. I don't know what it said that for. On the question online, the answer, because I had the answer after it. I thought I read that it was 150.
150 increase.
Yeah, it said that the answer was after. I thought it said online, didn't it?
Okay, let me check it. Yeah. Sorry, what?
Because you're calculating percentage increase,
Uh-huh.
so it should be 150% increase.
Ah, okay, yeah, right. Okay, thanks. Okay. let's go to the next question. Question 5. Okay. So we have a dam. The width of the dam is 40 meter into the board, and it's made of the concrete. The weight is given to us, assuming that the density of water is 1,000 kilogram per cubic meter. Calculate the pressure force on surface A, B, and the atmospheric pressure is 100 kilopascal. Is there any question? Okay, cool. So we need to calculate the pressure force on surface AB, that is here. Okay, so just here I would write that because I need the length of the AB, you know that AB is equal to 60, 80. So AB would be 100 meter. Okay, just I will need it for the rest of the question. Okay, so the question is asking for the pressure force. So I need to calculate the force by multiplying the pressure by the surface area. The pressure is a result of the atmospheric pressure plus the hydrostatic pressure. The A is constant for both of these, so and the H that I need here is the HCG. You have practiced this a lot, I think, in your class. So F would be equal to the AT comes from here. AB is equal, AC is equal to AT. So I need the center of gravity, because this is the rectangle, the half of this would be the center of gravity. So I'm using AT over 2 as the height, and the area is, here is 40 meter wide into the paper, and I have calculated the other side. So the A would be 40 multiplied by 100. And this gives us the pressure force equal to 1.97 Newton, which is kind of 2 giganewton. You can solve this. This is the final answer, but you can solve this using the integrals as well. I'm going to solve the next question both ways using the rho GH and the integral. So I recommend you to go at home and to solve this question 5 using the integrals as well, and see if you can get the similar answer. Any questions? This is like a simple question. Okay. What time is it? So, next question then. Yeah.
So what's the 40 times 100 represent?
Yeah. This is the area, okay, in which this pressure is exerted on. In the question, we have the width equal to 40 meter, and I calculated the AB equal to 100 meter. So by multiplying this, I would get this surface.
Surface
Yeah.
area?
Surface.
Thank you.
Okay. Okay, final question. Question 6. So here it's asking us to find the hydrostatic force per unit width on the rectangular gate AB in this figure. Again, we can use the, I'm going to do it here, the F is equal to P dot A, and P is equal to rho GH in center of gravity dot A. So F would be equal to the density of water, 9.81. Okay, the important thing here is that the center of gravity would be in the middle of this plane. So this part is 1 meter, and the other part half is 1 meter. I need to use the 3 plus 1, which is 4 meter, as the height, and then multiply it by 2 plus 1. 2 plus 1 is the surface area of this part. Because it's telling us to calculate it per unit width, I'm using the 1 here, because it's telling me per unit width. Okay? So the F would be equal to 78.4 Newton per meter. Okay, this is the final answer. So for the other option that I can use the integrals to calculate the force, do we have any volunteers to come here and solve this for us? It's just one integral, it's not that hard. Anyone? Okay. Okay, so I'm going to do it here. Question. This second option. I personally always use the rho GH, but it's a good practice for you to use the integral form sometimes. So F on the surface, on the AB, can be calculated using P dA, and again, because it's asking us for the force per unit, which I would need to use W here. And the force is from A to B, so it's from 3 meter to 5 meter. It's from 3 meter here to 5 meter here. So 3 to 5. I know A is equal to W dot dy, rho GH dy. Rho G is constant. The integral of, okay, this is rho G y. Sorry. The integral of y is y2 over 2 from 3 to 5. So FAB would be equal to, rho is 1000, we have the G, and we are integrating from 5 to 3. So again, same as here, the F would be equal to 78.40. Okay, this is it. Any questions? Yeah?
I was going to ask, how come with this one we don't take into account atmospheric pressure as well, like in the one before?
Yeah, could you repeat your question louder? I can't.
So I was just asking, how come in this one we don't take into account atmospheric pressure, like in question 5?
Okay, so here, find it. First of all, it's telling you to find the hydrostatic force only, not the. It's just saying to pressure force, just the hydrostatic pressure force. Yeah. questions? We have time. Yeah.
You know how you can do both methods without one with integration, one without integration? Like you've done it twice.
Yeah.
Is there a situation where we're going to have to do one but we can't do the other?
Yeah.
So what's the situation where we have to do integration?
When the density is not constant, you have to do the integrate.
Okay.
Yeah.
Is that the
Density.
The density of the water?
Yeah, the density of the liquid that you're dealing with, whatever
Not
it
like
is.
the density of the game.
No. That's just the fluid part. Yeah. Yeah.
So how do you get W dy?
This dA here is the area, and the area of a rectangle is calculated by multiplying the width over the height. Okay? So, if I have a rectangle, what you're seeing here is like this, and you have to look at it like this. So, I have D here, and then the height, the others. Okay? Yeah?
Could you run through the integration methods for the previous question?
Previous question, question 6, you mean?
The previous one where you said you can do the integration method.
Okay. Yeah, I can, but I want you to try it first. Yeah. You can try it, and if you couldn't get the good the final answer, ask it on Piazza. I will help you there. Okay.
So, for question 4, is the answer like 1.5 times the original height or 2.5 times the original height?
Question 4. $1.5.
Because I found 2 pounds only. Yeah, it's it's 1.5 to the original height, it's only a quarter something.
Okay, so if you are finished, the class is over. If you want to go, you can go. But if you have any questions, I'll be here to answer the questions. So, the question is question 4, right? Is telling you that the first question is 150. That would be that 5%
Oh, so plus 1.5.
Two, this is the height of this part, okay, and one because we are calculating perimeter width. We consider the width equal to 1. So the area of this part will be 2 multiplied by 1.
یک و نیم که شما به دست آوردید ضرب در آن میشه 150% میزان فشار اولیه ما، چون اگه 150% اینکریز داشته باشه میشه 2 برابر و نیم.
ما الان داریم اشون می‌ذاریم مثلا فشار رو بکنیم بعد من این الان خودم اینجا الان اشون مناقش رو باید کردن از این عملا فقط اینکریز رو داریم
اینم توضیح
اوکی سو اینجا این آلفاس خب ما آلفا رو می‌خوایم اینجا اول تا اینجا یه اویل داشتیم الان اینجا با این بهش بشیم پس سطح اویل اینجا میاد پایین اینجا میاد بالا درسته اون حجم اویلی که اینجا رفته پایین دقیقاً همون قدر این رو به اضافه شده خب این حجم اویلی که اینجا رفته پایین چقدره؟ آ دلتا
ایا رو برابر کنیم
نه ای دلتا اچ
ای دلتا اچ میشه
اریا ضرب در ارتفاع که میشه حجم درسته؟
حجم
حالا این مساوی حجم که این بر اضافه شده دیگه این ارتفاع دوباره اریای ضرب در ارتفاعی که حجم تو این بر اضافه نشون میده با مساوی قرار دادن این دو تا حجم من میتونم بیام این دلتا اچ رو حساب کنم چون دی رو دارم آی پیش دارم رو بذارم حالا که دلتا اچ رو دارم میتونم ازش فشار رو حساب کنم Yeah, this is because it's only 5 millimeter. It's so small. The difference is so small that you can just assume it's constant. Yeah, good question. Really good question.
Sorry, if you don't mind, can you just quickly go through that question? I
Question 3.
Your calculation.
Question 3.
The one with inclined plane manometer.
3.
Yeah.
Okay.
Yeah.
Okay. So, we have a manometer here in constant state. Okay. Now I'm increasing the pressure in this area. Because I increase the pressure here, the liquid here has to go down. Okay. So. But the liquid can't just disappear, right? From here, it goes to here. So the amount of the oil that has been displaced from this area, this part, is added to this part. Yeah. But how can I calculate this volume? So I have the diameter of this circle, so I can calculate the area of this circle and then multiply it by height, so I would get the volume. Okay? So that amount of volume is exactly the amount of volume that has been added to this part. So again, I have the diameter so that I can calculate the area, and using the area multiplied by the D,
so
I can calculate the exactly. I can calculate
Okay, and then after we get the change of height from the difference of area.
Yeah.
How should we continue from there?
Wait, let me find it. Question 3 was it?
Yeah.
Thanks. Yeah. Okay. So here I got the delta H equal to D over 4 using this the volume, the equality of the volumes. So now I want to calculate the PC here. Okay, because the surface has gone down, right?
Okay.
So I have the PB, which was the initial free surface. Now, if I add the hydrostatic pressure of this part to B, I can get the pressure at C. So PC would be equal to PB, which I initially calculated, plus the rho G delta H, and delta H is D4.
I see. But why do we add the pressure? It's not like
because C is lower than B, so the hydrostatic force on the liquid on top of it has to be taken into account. Yeah.
Okay.
So you would, using this, you would get sine alpha, and using the sine alpha, you would get the alpha.
Okay, I see. Another question: how do you know that the width is equals to 1? The question where we got of this thing. Yeah.
is said in the question. Find the hydrostatic force per unit width.
Also, because
you
of
have to
this,
take
you
it
take
one.
it one.
Whatever it is, you have to take it one.
I see. Thank you.
You're welcome. Any help?
I just want to snapshot
Of
question 3.
Yeah. Is the solution to the tutorials added on Blackboard?
Yes, correct. It's uploaded.
Okay.
Yeah.
Okay.
Thank you.
Welcome. Hi.
This is more of a theory question.
Yeah,
just as well. But, you know, control volumes, right?
Uh-huh.
And, so we have this control volume here, right? It's flowing at an angle. And here's N, the normal, yeah. Why, when finding the flow, the amount of flow here that's coming in at this angle, why do we have to do it in terms of N? Why do we have to do cos N or
I
cos
think
theta?
you're talking about the divergence theorem. You want to change the integral over a volume to integral over a surface.
Right.
Is that what you're talking about?
I mean, I'm not sure, but
Yeah.
it's just that like,
This is what we do in the divergence theorem. I'm not sure if you're talking about that.
right. Well,
But there, because, you know, control volume is talking about the volume. Okay?
yeah.
So, volume is hard to deal with. We have to change this integration over a volume to integration over a surface.
Yeah.
And because of that, we do that to change it.
No, yeah, I get that.
Okay.
If it hits a surface at an angle, like, well, to the normal,
Mm-hmm.
then
Yeah.
why even do it in terms of the normal? Why not just find, you know, the V dt dA
Okay, so
or V
I need
dA?
more details. I don't know what this is. So if you could just take a screenshot of it and put it on Piazza, I will have it.
Okay. Also, Miss,
Kalau ikutkan yang soalan 6 tu dia buat
this
situ kan.
equation here, this is related to control volumes again.
Okay.
W.
dV is V cos
Omega.
theta dA dt.
Uh-huh.
It's
dy.
the volume.
How come
volume.
how come you have 1D here but 2D here?
Oh, it's just what it says on the book. Yes.
Okay.
And
Because here again, look, you have only dA.
yeah, that's what I was wondering. Like, where did the dt go?
Okay.
This thing, this bit there.
I don't think it shouldn't be here.
It should not be.
No, you cannot have one parameter here and then two integrals here.
I'll double check that.
Yeah. Okay.
Okay. Thank you.
Yeah. Okay. Hi.
Yeah.
Hello, I want to ask about this number 5.
Number 5. Okay.
So that's you can use integration to